Hi guys, welcome to the video for 5.3.1 where we're looking at electric cells. This is a fairly short chapter, but we will split this into two parts, so let's begin. All right, quick little overview of this chapter on cells is we're looking at the way cells transform energy and also the limitations of cells in their ability to transform energy. So our first learning objective is to distinguish between primary and secondary cells. So this is pretty straightforward. Primary cells, we have disposable cells. Primary cells are disposable, and secondary cells are reusable. Okay, and by disposable, we mean that they can only be used once. We throw it away, it goes to landfill, and not the most environmentally friendly thing. They cannot be recharged. And so that's hence why they are disposable. They're used up and that's it. Whereas secondary cells are rechargeable. And primary cells have, their electrochemical process cannot be reversed. Whereas because of the nature of them being reversible, of course, that also means their electrochemical process is reversible in the secondary cells. Okay? A typical name for primary cells are dry cells, which leads to sort of the nature of them not having liquid type substances inside of them. Now, the common everyday term for what we call cells in physics is a battery. And a battery then takes on a new definition in physics where it consists of multiple cells. And so we'll talk more about batteries next lesson. Our second learning objective is to understand that cells reduce their voltage as they are used and to describe a typical characteristic for a simple cell. So this table I borrowed from Cognitive 5.3.1. And for this first activity, I want you to think about, compare the three lines, the 3.9 ohm line, the red one, the 24 ohm green line, and the 62 ohm blue line. So what does the trend suggest to you? Think about how does resistance affect the service time? Okay, so resistance, how does that affect the service time? Okay, so hopefully you've paused the video and you've had a chance to think about that and come up with a trend either mentally or you've written it down. It's quite obvious from the graph that as the resistance goes up, so we have an increasing resistance over here, the amount of service time also goes up as well. So there's sort of a positive correlation between resistance and service time. And for any cell, the voltage will continue to drop no matter what, okay? It's just the rate at which that voltage or potential difference drops. And it's because of the amount of current being supplied. So when the resistance goes up, so that's the part in green, when the resistance goes up, the current has to come down. And so because the current goes down, it doesn't draw as much current anymore. And so the voltage goes down at a slower rate. Our next thing to think about is to look at the area underneath the graph. And there are two different quantities that we can identify, voltage multiplied by times or charge multiplied by resistance. Now, I'm going to take a moment just to review the idea of how to solve graph questions. So we're going to look at this graph in terms of how to solve graph questions. And we never really had a chance to talk about this. So what we want to do is we want to count the number of rectangles underneath a graph. And so I'm going to count the green one because, well, it's a little bit more obvious. There's some easier ones to count. So I'm going to start from the bottom. I'm going to start with the whole. Okay, so that line technically goes there as well. So there's definitely 1, 2, 3, 4. It's kind of weird counting up. 4, 5, and then 6, 7, 8. I'm just going to count all the absolute ones. Okay. Now for the other ones, we can kind of ballpark that there's going to be some overlap. So I'm going to sort of say this one and this one is going to form 10. And it sort of looks like this one and this little bit over there, I guess, could form an 11. And then I suppose this part and this part could form a 12, okay? So we have sort of like 12 and a half maybe. So what will be in the solution will be anywhere between, they'll probably give you a slightly wider range in this, so they'll probably do something like 11 to 14 would probably be the acceptable ranges. But if you did a pretty good job and you kind of put together the halves, you should get a number that is within the range. And so we have 11 to 14 units. What are these units? So each of these units is what one rectangle represents. So one rectangle represents 0.1 volts multiplied by 20 hours. So we have 11 to 14 units of this, okay? Oftentimes they'll ask, this will be converted into an actual physical quantity, but here we don't have an actual physical quantity, but usually this forms into some other like single quantity like time or seconds or distance. Okay, on to our third learning objective, which is to describe how to connect secondary cells in order to recharge it. So pretty straightforward, positive to positive, negative to negative, and that's pretty much it in terms of this learning objective. Now, I've decided to extend the knowledge a little bit further and talk about phones because you want to make sure you use a commercial charger. And the commercial charger, you'll notice that is that it sort of slows down as it reaches 90 or 90+%. So you might notice when you're charging your phone, it charges maybe from like 40% to 80% really, really fast. It takes like half an hour to charge that. But then for the last 20%, especially that last 10%, it takes a lot longer. So what's going on there? And the reasoning for that is that with rechargeable or secondary cells, as it reaches its maximum percentage or maximum voltage, it needs to slow down the rate of charging to protect the cell from overheating, or as we commonly like to say, prevent it from exploding. Okay, and of course, overheating it will cause the cell to expand, thereby causing it to explode. So there is a reason for the phone to slow down its charging as it reaches maximum capacity. So it's not really worth it, you can say, to wait for that. I mean, if it's plugged in overnight, then you know, there's no loss of time, obviously. Okay, on to our last learning objective, which we're looking at calculations. So this is actually looking at how an amp hour is equal to a coulomb. So an amp hour is the units is equal to a coulomb. Now, hour here is sort of a little bit misleading. It's not necessarily a one-to-one ratio. And what we're actually seeing here is that if we took our fundamental formula, so essentially 1 coulomb would be equal to 1 amp multiplied by 1 second. That is true. But when we arrange this to amp hours, what we're doing is we're multiplying seconds by 3600. So there's 60 minutes in an hour, and there's 60 seconds in a minute. So when you multiply the two together, you get 3,600 seconds per 1 hour. Okay? So 1 amp hour is actually equal to, so 1 amp, I'm going to write this as 3,600 seconds, which is the equivalent of 1 amp hour, is equal to 3,600 coulombs, okay, or charges, as we might like to say. Okay, so the charge of a battery, 3,600 coulombs, is 1 amp times 3,600. Okay, so let's get into some calculations here of our question. Okay, so example number 1, secondary battery for an electric drill uses 18 volts of nickel metal hydride battery rated at 2 amp hours, and the drill is used continuously for 3 hours, at which time the battery is fully discharged. So the first question asks us to determine the full amount of charge originally in the battery. And so that is literally just taking our example right here, and we're going to plop that down into here. So we're trying to determine the charge, and we've got the current which is, oh, sorry, yeah. The current is 2 amps, and per hour, so 1 hour, we then have to remember convert that into seconds. So this is 3,600 seconds. So first off, I'm just going to write 1 hour equals 3,600 seconds. Okay. So this whole formula does have to work with time being in seconds, which is why we have to convert this into seconds. So that's 3,600 seconds. And when we multiply the two, we get 2 amp hours. And so we already saw that 1 amp hour is 3,600 coulombs. So 2 amp hours is double that. 2 times 3,600 is 7,200 coulombs. Okay. And next up, determine the average current through the drill during this period. So average current. So it's working on 2 amp hours, and this is happening over 3 hours worth of time. So again, 3 hours is worth 3 times 3,600. So in terms of time, we're looking at 1080 seconds in terms of time. Okay, so really we're operating at average current. So what we've got then is we have the current we're trying to determine. So I'm going to write Q equals to IT. And we're trying to determine current with the total amount of charge it has per unit of time. So this up here is how much charge the full battery has. 7,200 coulombs of charge. This is being stretched over 3 hours, which we just converted into seconds there. So 10,800 seconds. And so 7,200 divided by 10,800 is 0.67 amps. So this is the average current flowing over the 3 hours. Okay, we're taking the 7,200 coulombs and extending that over 3 hours worth of time, which is 10,800 seconds. 10,800 seconds. Okay, lastly, calculate the energy transformed by the drill. So the energy is going to be work. So current, is it current? No, potential difference. Potential difference is work per unit charge. Work per unit charge, but this is little q, so this is not really the right formula to use here because this is talking about small point charge. So I think we might need to look at something like power then, is current times voltage. So power is the work done per unit time is another way to think about this. Okay, so now we've got the relationship. Okay, so IV equals to work per unit time, sorry. Power is work per unit time, sorry, I messed that up. That's divided by time. Work per unit time. So IV equals to work per unit time, the rate at which work is done. So then we have essentially V times the change in time is going to be the work done. So we know that it is 18 volts, and we have the other two pieces of information. So time, we're going to borrow that from earlier, which is a total of 3 hours, or 10,800 seconds. Okay, so make sure all the units align. The current is 0.67, we just calculated that earlier, 0.67 amps. And the voltage is 17 volts, and now we have our work. So 17 times 0.67 times 10,800 is 123012. And if we want to sig fig that, that would probably be two significant figures. So 12 times 10 to the power 4 joules. Okay guys, that's it for today. This first part was kind of easy, and we will dive into probably a longer video next time when we look more at cells. Okay, see you guys next time.